In this video, I'm going to show you a toy code implementation of DeepSeek R1 Zero. So this is the paper which introduced DeepSeek R1 Zero, DeepSeek R1, as well as some distillation models. So this paper covers basically three important things. So DeepSeek R1 Zero, which was created by implementing reinforcement learning on a particular base model. So the base model was already pretty impressive. And if you use reinforcement learning on top of a decent base model, you can get reasoning capabilities. And that's what DeepSeek R1 Zero was about. Then there were some drawbacks with DeepSeek R1 Zero, which is why they created DeepSeek R1, where you use reinforcement learning from a cold start. And later they did distillation to empower small models with reasoning capabilities. So three essential things was done here. For this video, I'm going to focus only on DeepSeek R1 Zero. So basically I will try to mimic the training code which might have been written in this case. And my code will have a very basic base model. The idea is that I should be able to run it at least for few steps in my own laptop or Google Colab, just to give you an overall flavor of how it might feel like. Okay, so here they have written their contributions. Here they have written, we directly apply RL to the base model without relying on supervised fine tuning as a preliminary step. This allows the model to explore chain of thought for solving complex problems, resulting in the development of DeepSeek R1 Zero. Okay, so chain of thought automatically emerges from their technique of RL. And I'm going to write a toy code which essentially will try to do this. And in DeepSeek R1 Zero section, they have mentioned they are exploring the potential of LLMs to develop reasoning capabilities without any supervised data. Okay, and here they are using reinforcement learning algorithm where they're including group relative policy optimization algorithm, and also they have a proper prompting mechanism where they create a system prompt which essentially asks the LLM to think and then give an answer. Okay, so the overall idea is that we ask it to think and give an answer, and we will only reward it if it follows this pattern, and we will not reward it if it doesn't, so that the model has no other choice but to actually think and then finally give an answer. Okay, so this is the toy code implementation that tries to mimic the training process of DeepSeek R1 Zero. The key components which the code has from the paper are the following. So there is this direct reinforcement learning training without supervised fine tuning. That is GRPO, group relative policy optimization for policy updates. There is rule-based rewards for accuracy and format. So both accuracy and format are rewarded. So we want the model to think in certain way, which is why we're rewarding the formats as well. And the think and answer template for structured outputs. So we are basically asking the model to format its responses in certain way. And of course, we are going to reward if it does follow that. And we are not going to reward it if it does not follow that. Then hopefully the model will be guided in that direction. Okay, so there's some initial setup and we are checking for CUDA if it is available. Then we are using this model. So it's a OpenLlama 3 billion parameter model, which is relatively small. At least it will run on your laptop or on Google Colab. And then we have this function to load the dataset. And here the actual dataset, the reasoning dataset, the mathematical reasoning dataset is way bigger. So we are only trying to train it for the first 20 rows of the dataset, not the whole dataset, because we don't have RAM or memory for that. We also need some form of quantization to ensure we are reducing memory usage while maintaining performance. Without that, it will simply blow up. You will not be able to run at all in Google Colab. So we're using bits and bytes config to do some quantization. So let me start with the main program and then I will show you the individual functions. So this is the main program. Here we're doing the standard stuff. So we're initializing a tokenizer from the Llama tokenizer. We're initializing the base model. And then we are pre-processing their dataset. I will get back to that later. We need some pre-processing in the dataset so that it is in the required format in which we want to train it. We can't simply dump the dataset in random format and expect it to perform the way we want. Then here essentially I'm just printing how the base model is by default without any reinforcement learning. Okay, so that we can eventually compare with how it ends up with. And now we have this trainer, which is the GRPO optimization trainer. I'll get back to that bit later. So I'm going for 10 epochs, and in each epoch I have this training step, and I'm checkpointing it periodically as well as printing after every epoch how the model behaves. Okay, so now coming to the pre-processed data set. So here we want certain things. We want a system prompt that explains the task. The task is that the model is supposed to think in a reasoning capability. Okay, and then the prompt should have the question and the expected response using this think and answer tags. Okay, so first we are looping over the entire data set, and then we have the system prompt, which says a conversation between user and assistant. A user asks a question, the assistant solves it. The assistant has to think initially, and then the reasoning process needs to be inside think tags, and the answer has to be inside the answer tags. Okay, so this is like the system prompt. And then we take out the question and answer, and we also take out the numeric answer. And then in the full prompt, we have the system prompt followed by the question. And the formatted answer is the answer within the think tag and the numeric answer within the answer tags. So this is the way we are structuring our input data. Then next comes compute reward function. So we want to reward correct answer as well as correct way of thinking. So here we have format reward, where we are ensuring that it has think tags as well as answer tags. So the fact that it thinks and actually produces an answer, not just thinks or not just produces an answer. And then of course there is accuracy reward. So if it is giving correct numerical answer or not. So here it checks if it has think tags and answer tags, and accordingly the reward gets added. And then we are essentially matching the pattern of the answer as well as the numerical answer, and then calculating the reward and returning the reward. The evaluate model is just a helper function here, where we give it a prompt and then just simply print its output. So we have the tokenizer. From it we get the input IDs, and then we call model.generate to generate outputs. And here we need to do decoding to get the actual response in text format. And then we are simply printing it and checking if it is giving structural analysis or not, or if it is giving a thinking process or not, or giving a final answer or not. And here we have the class DeepSeek trainer, which is the key component here. So this implements the GRPO optimization. So the key features are it uses GRPO for policy optimization of the reinforcement learning program. It maintains a reference model for stable training. And it also has this clipped objectives, which is mentioned in the paper. So at the heart of the reinforcement learning algorithm, which is mentioned in the paper, lies the group relative policy optimization, called as GRPO. So here, group relative policy optimization. So first of all, it's an optimization algorithm. So any optimization algorithm needs to have an optimization function. And this is the optimization function, this JGRPO theta. Okay, so I will briefly explain what exactly it is trying to optimize and each of these terms. So at every step, what we want to do is to steer the current model with the current set of parameters in such a way that it starts to become better and better. Okay, so let's say the current set of parameters are theta, which is why this optimization function has this argument as theta. So this theta represents all the weights inside the entire transformer or GPT architecture, right? So it is essentially an expected value we are calculating. So E stands for the expectation, which is roughly, let's say, the average. And average of what? So, or average over what? So we have, let's say, a question called Q, and the GRPO samples a group of outputs. So we can have, let's say G is equal to 4. That means we'll have 4 different outputs from the old policy. Okay, so the policy here essentially represents the LLM, which is evolving. Okay, so the LLM itself is the policy, and pi is the probability. So the probability of certain output. Okay, so here let's say this term, this is pi theta OIQ, which means what is the probability of this output OI given this question Q. Okay, for the theta weight functions, theta parameter. Okay, so that is for theta. For theta old, we also have the same thing. So old is the old policy and theta here is the new policy. So is the new policy, how does it compare with the old policy? We're simply dividing these two and multiplying it with something called advantage. Okay. And what is the advantage? The advantage essentially measures if an output is better than average. Okay. So here this Ri is the reward. So how much better the reward is compared to the average. And this is just a standardizing term. So we multiply that with this term to get an overall idea of whether we are heading in the right direction. So if this entire term is going up, that means the new policy, the pi theta, the new policy, that is more likely to generate a better outcome compared to the old policy. So we should move more towards that direction. Okay, we eventually want to increase the j, and this value, if that increases, then j increases, which means we are heading in the right direction. Okay, and this clip function ensures that we are not deviating too much compared to the old policy. Otherwise, we may end up in way outside of local minima and the update might be uncontrolled. Okay, so we want to do control updates in the right direction. Okay, so here's this min function and it is taking the minimum of these two. And then we have another parameter here, which is called the KL divergence. And this essentially penalizes if we move too far away from the reference policy. So the overall idea is to maximize the advantage, which means get good responses and at the same time do stable updating using the clipping term and staying near the reference policy at the same time. Okay, so it's a very controlled way of improving the overall model. And then the optimization process, what it does is it generates responses using the current set of weights represented as theta, then calculates loss using the GRPO formula, then the usual neural network stuff, the back propagation. It does back propagation through the network, and then it updates theta, which is the weights, using the Adam optimizer. So this is the whole optimization process, and this is the corresponding formula. So to give an example, let's say this is the formula, and let's say here we have a question. So let's say the question is what is 5 plus 7, and we have OI where each of these OIs are the responses. So if we take G equal to 4, that means we have a group size of 4 and our model generates 4 responses. Okay, then we have this 1 by G over term, which is supposed to average things out. And as I said before, pi is the policy, which is essentially the probability distribution of what tokens will the model generate given the previous tokens. Okay, so OI by Q here. So Q is the previous ones and OI are the new ones. So probability distribution of what OI will be generated given Q. Okay, so that's what it says. Pi O slash Q is the probability of generating output O given input Q. And this is for the current parameters. And we can do the same for the old ones and take the ratio. Okay, so the probability ratio between new and old policy. So for instance, this will be the probability of generating, let's say the response will be like this, add 5 and 7 ... 12 with the new policy, divided by probability of generating the same with the old policy. And as I mentioned before, the advantage term, which is essentially getting multiplied with this ratio, that talks about how much better or worse each response is compared to the average response. Okay, so here are some numerical values to get a better understanding. So let's say there are 4 outputs from the model and they have rewards such as 1, 1, 0.4 and 1. So we calculate mean and standard deviation, and we can then calculate advantages A1, A2, A3, A4, where a positive advantage means better than average and negative ones is worse than average. So that means we should favor those outputs which are better than average. And we have a clipping mechanism which prevents too large changes. So if epsilon is 0.2, we ensure that clip ratios are between 0.8 and 1.2. And finally, the KL divergence term, which essentially ensures that we penalize if a new policy diverges too far from the reference. So here we have this optimization function where we need to calculate the response of the model at various steps and compare it to the old responses and see if it is better or not. And then we also don't want it to be going too far ahead from the older model, which is why there is a clipping mechanism in place. So to summarize, GRPO typically averages out over a group of responses to know if a new policy is better than the old one and optimize accordingly. Okay, so the new policy, the new way the model parameters are evolving, if that is better than the old way the parameters were there, okay, and optimize accordingly. Okay, now let's move to the trend step function, and this essentially implements the GRPO algorithm. And what does the GRPO algorithm do? It generates multiple responses for each prompt, compute rewards and advantages. I will explain what those are, and then updates policy using a particular objective function based on the rewards. Okay, so we have the training loop going on, and here for each of the data set we get the corresponding prompt, the correct answer, and we also keep track of old samples and old rewards in line with these old parameters which we have here. And then we have a loop for the group size. So here group size means the G value here, which let's say it was 4 in this example. So 4 times we generate IDs. We generate IDs by calling the generate function of the model. Then we also create the generated text by decoding it. We calculate the reward, and we save the samples as well as the reward for historical tracking. And then we calculate the advantage term. Okay, we calculate mean, standard deviation, and the advantage based on the formula here. And now we have the old samples and advantages. We are eventually going to calculate the overall loss. So now we are calculating here the pi's which are here. Okay, the pi theta divided by pi theta old. So we have the output here. We calculate the logits and the corresponding log probabilities, because pi is the policy, which is the probability distribution over what the model will generate given the previous tokens. Okay, so here the probability distribution is this softmax function here, and we calculate the overall mean of the probabilities. Then we calculate the ratio, which is here, the unclipped objective, which means the ratio times the advantage, which is the first term here, right? As you can see, this is the ratio times advantage. Now we have to calculate the clipped objective. So the clipped objective, we have to clamp it here. We have to use epsilon here. Here is the epsilon of this term. Okay, and we calculate the policy loss. So the policy loss, what we are doing here is this J needs to be maximized, but in our code we are minimizing the negative of that. Okay, so here is the negative term, it is coming. And then we also have to add the KL divergence term, which is this value. Okay, so beta times DKL, and that gets calculated here. We are setting beta here, and then we're adding that to the loss, and then we are using back propagation and optimizer to optimize the weights, the model weights. Okay, so this is the very important GRPO trend step. Okay, we change the runtime type to the GPU, and we first install the dependencies. Okay, now that the dependencies have been installed, let's just run the entire training code. Okay, now it's loading the model. After that, it will process the data set with the format we want, do an initial evaluation to see where the base model stands as it is, and then it will initialize a trainer and start the training loop. So the sample question is that Natalia sold clips to 48 of her friends in April, and then she sold half as many clips in May. So how many total clips did Natalia sell altogether in April and May? Obviously, it's a relatively challenging mathematical problem for an LLM. So the base model before training, so this is the input prompt and this is the corresponding model response. Okay, so obviously we're not expecting it to actually answer it. It simply keeps on, talking. So she sold 48 clips, 48, 96. She keeps on, the model keeps on randomly guessing. And then eventually it forgets about what it does. And now the training has started. We're at epoch number 1. And now the RAM will start increasing. We only have like 15 GB. So maximum we are going to have 2 epochs here. The idea is we are at least going to see some difference. So here after one round, we are at least seeing different numbers. So it's at least guiding the base model in some direction, perhaps. So the numbers before we saw were like what 48, 96. Now we are seeing 87, 171. And now we're moving to the second iteration. Okay, we are in the first epoch and it's just starting out. We have what, 28 data sets, so it's starting out with the first one, then it's going to the second one, and yeah, the RAM limit will be hit anytime soon. But at least we saw some difference compared to the base model. And obviously, with this base model, we don't expect it to do much far. Even if I had, a lot more RAM, it, I'm still not expecting it to actually start thinking. For that, we need to have a much better base model. But I guess we'll see. If you have more RAM, then feel free to run this code and maybe you might be able to find something cooler. Okay, now as suspected, it has run out of memory at the first epoch's second training step. Essentially, we can see here it is hitting the memory limit now.